Hello, this is Madan Bibi from Sri Venkateshwara College of Engineering. Today I am going to discuss about Introduction to VLSI Fabrication. Very large-scale integration is the process of creating integrated circuits by combining thousands or millions of transistors into a single chip. This advanced fabrication technique has revolutionized the electronics industry, enabling the production of powerful and compact devices like smartphones, computers, and modern electronics. The VLSI fabrication process involves a complex series of steps from water preparation to packaging that require precise control and cutting-edge technology. Semiconductor materials and water preparation. Silicon, the workhorse. Silicon is the predominant semiconductor material used in VLSI fabrication due to its excellent electronic properties, abundance, and well-established manufacturing processes. It forms the backbone of modern integrated circuits. Water fabrication. Silicon wafer fabrication. Silicon wafer are produced by growing high purity single crystal ingots and then slicing them into thin polished discs. The wafer size has steadily increased over time, enabling higher chip densities and economics of scale. Doping and epitaxy to create the necessary p-n junctions and control the electrical properties. The silicon vapors undergoes doping with impurities. Epitaxial growth techniques are also used to deposit thin high-quality semiconductor layers on the water surface. Photolithography process. Wafer preparation. The process begins with a clean silicon wafer which undergoes various cleaning steps to remove any impurities or contaminants. This ensures a pristine surface for the subsequent photolithography steps. Photoresist coating. A thin layer of photosensitive materials known as a photoresist is then spin coated onto the wafer. The photoresist is carefully chosen based on the desired pattern and resolution requirements. Exposure and development. The coated wafer is then exposed to a specific wavelength of light through contains the desired circuit pattern. The exposed or unexposed photoresist coating removed during the development process, creating the desired pattern. Thin film deposition techniques. Evaporation. Evaporation is a common thin film deposition technique in VLSI fabrication. It involves heating a source material until it vaporizes, then condensing the vapor onto the substrate to form a thin film. This method allows for precise control over the film thickness and composition. Sputtering. Sputtering is a physical vapor deposition process that uses energetic ions to dislodge and eject atoms from target material. The ejected atoms then deposit on the substrate forming a thin film. Sputtering provides excellent step coverage and can be used for a wide range of materials. Chemical vapor deposition. In CVD gases, precious chemicals are introduced into a reaction chamber and on substrate surface depositing a thin film. CVD can produce high quality, precise thickness and composition control, making it crucial for VLSI fabrication. Ethicking and doping process. Chemical ethicking, selective removal of materials using wet chemical solutions. Plasma etching, anechotropic ethicking using chemically reactive ionized gases. Ion implantation, doping semiconductor materials with high energy charged particles. Ethicking and doping process are critical steps in VLSI fabrication. Chemical and plasma ethicking techniques enables the precise patterning of materials on the wafer surface. Ion implementation is used to selectively introduce the impurities into semiconductors, creating the desired doping profiles for transistors and other devices. This process must be carefully controlled to ensure the integrity of the integrated circuit structures and maintain high manufacturing. Metallization and interconnect layers. Interconnect layers. Multiple conductivity layers typically made of metals like copper or aluminum are used to connect different components and devices on a VLSI chip. These interconnect layers are essential for the signal routing and power distribution throughout the integrated circuit. Thin film deposition. The metallization process involves depositing thin films of conductivity materials such as metals on the semiconductor wafer. Various deposition techniques including sputtering, evaporation, and chemical vapor deposition are used to create these interconnect layers with precise thickness and composition, patterning and etching. After the metal layers are deposited, they are patterned using photolithography and etched to form the desired interconnect structure. This allows for the creation of complex routing networks that connect different components and devices on the VLSI chip. Planarization and polishing techniques. Chemical mechanical polishing CMP. Remove excess materials through combined chemicals and mechanical action. Spin on dielectric planarization. Deposits a viscose dielectric layer that is then spun and hardened. Resist etchback planarization. Etches back a photoresist layer to create a flat surface. Packing and assembly. Advanced packing techniques. VLSI chips requires intricate packaging to protect the delicate security and facilities connections to the outside world. Advanced packages methods like ball grid array and flip chip provide high density interconnects and robust mechanical support for the chip. Automated assembly process. VLSI fabrication culminates in the assembly of the packaged chip onto a circuit board or module. Sophisticated robotic systems carefully place and solder the chip using precise high-speed automated processes to ensure reliability and consistency. Rigorous testing and validation. Before a VLSI chip can be shipped, it undergoes extensive testing and validation to ensure it meets all performance and reliability requirements. This includes electrical testing, thermal cycling, and environmental stress screening to catch any defects or weaknesses. Yield and reliability considerations. Maintaining high yield and reliability is crucial in VLSI fabrication, as even minor defects can lead to significant losses and failures. Factors such as a process control, clean room environments, and robust testing procedures are critical in ensuring consistent and reliable chip production. Yields refer to the percentage of functional chip produced from a wafer, while reliability considers the long-term performance and lifespan of the devices. Advanced statistical process control techniques, rigorous contaminations, monitoring and comprehensive testing at various stages of the fabrication process help maximize yield and ensure the durability of VLSI chips. Additionally, a design for testability and design for manufacturability principles are implemented to improve the overall fabrication process and reduce the likelihood of defects by continuously optimizing the improving these considerations. Semiconductor manufacturers can deliver high quality, reliable VLSI devices to the market. Future trends in VLSI fabrications. As the semiconductor industry continues to push the boundaries of device scaling, the future of VLSI fabrications holds exciting advancements. Emerging technologies like extreme ultraviolet lithography are poised to enable the creation of ever smaller transistors, allowing for increased chip density and performance. Additional innovations in material science, such as the use of novel dielectrics and high mobility channel materials, will enable further devices scaling and power efficiency improvements. Parallel to these technologies, breakthroughs, the industry is also exploring alternative fabrication approaches, including 3D integration and chiplet-based architectures, to overcome the challenges of traditional 2D scaling. Behind device scaling, the future of VLSI fabrications also encompasses advancement in process automation, yield optimization, and sustainability. The continued development of machine learning and artificial intelligence algorithms will enable smarter and more efficient manufacturing processes, improving overall yield and reliability. Additionally, the industry is placing greater emphasis on reducing the environmental impact of semiconductor manufacturing through adoption of more sustainable materials and energy efficient fabrication techniques.